Welcome back. The plan for today is to go over chapter 3. I hope that you have time to look at the material that we've seen yesterday. And also I hope that everyone now has access to the material on the Dropbox or on the website. We can put the link again in the conversation at some point. So I'm going to turn over to the board camera now. Okay, so this is in my notes, chapter 3. So yesterday we've seen chapter 2 on discrete time Markov chains, which is a nice topic to start with because it's just simpler in terms of notation. But the problem with Markov chains and discrete times is that we have that discrete time, which is not quite physical. So as physicists, we like to have something that evolves continuously in time, which is what we'll discuss today. So the picture that we have that we want to cover today is that we have a certain state. So that's a random variable that is indexed with time. So that's the stochastic process. And then we have a certain number of discrete states. And then we start at some states and then we can stay there for some time, some random time. And then we'll have a jump to another state and then we'll stay there with some random time. And we'll have another jump, maybe another jump, and then maybe another jump. So this is time, and time is continuous now, and then we have these jumps to different states. Okay, so this can represent different things. If you have two levels, two states, it could be what we discussed in terms of laser. You have a ground state and some excited state, and then you stay in the ground state for some random time, and then you have a jump, a random jump to the excited state, and then you can come back after some random time. So what's important here is that we have these random times, which we'll call the residence time or the occupation time. So you stay in some state for some random time, and then you jump to another state, some random state that you choose at random, and then you stay in that state for some random time too. So here, if I denote all these random times, I have tau 1, tau 2, tau 3, and then so on. So this is more physical because we have that continuous time and then we have that continuous time evolution. So I want to describe this as a Markov process. And what we'll see now is instead of focusing on that transition matrix that we were discussing yesterday, what we'll have is a bunch of transition rates. And then to define the Markov chain, we just have to specify the transition rates, and that will define the transition matrix. So this is where we're going with this. Okay, and again, maybe just to fix the idea. So what we have here now is discrete set of states. Tomorrow, actually, we'll go into continuous state, but we're staying now with discrete state of state. And we have that thing now, we have continuous time. And then, so this is why we call this a continuous time Markov chains, but these processes are also called often jump processes. Okay, because what we have is a bunch of states connected by random jumps. Okay. So what I'll do now is to define actually what we mean by a Markov chain in continuous time. And I introduced that notion of transition matrix that we've seen yesterday, but now we'll actually generalize that transition matrix to continuous time. But we'll get to see that the transition matrix is not so convenient. What's more convenient are the transition rates. And so I'll go to the transition rates. And after this, we'll see how the propagation equation that we had yesterday is generalized to continuous time. And then we'll see some examples. So I'll go straight with the hour and a half. And I'll go from the theory to the applications at the end. And feel free to ask questions as we go along. Okay. So let me go into defining now that Markov chain in continuous time. This is section 3.1 in the notes. Definition. So we have a process. So that's the process x indexed by t. And now t is a real parameter, which for us will go from 0 to some capital T. So that's the trajectory that I have here from time 0 to a certain time capital T. And then the variable, the index time, is the lowercase t. We have a certain state space. which often I'm not going to actually define. So that process takes value in some state space. That's the state space. And now I'm going to define the Markov property. So the Markov property that we had yesterday was that if you look at a present time and you look at the future, the transition to the future does not depend on anything that happens before present. So here we're going to have the same, but it's just slightly more technical to write down because we can pick up any time here. So what I'm going to do is I'm going to write the probability for the state to be going at some time Tn, so this is the probability to be jumping at some state J, given that I have some previous time, so T1 maybe is I1, then I have many T's, maybe x Tn minus 1 is I minus 1. So if I look at the future, and then I have a sequence of states and time, the transition will only depend on the closest to the future, and that will be the present. So this will be the probability of jumping Tn to J, given that I have the closest time to it to be, so actually here I have, let me put just I here, so this is easier. Then here I have I. Okay, so let me draw this. So if this is true for all I n minus in I1, and then the j, and all times where you have 0, you have the T1 here, Tn minus 1, and then the Tn. So what we have here is, if you look at time, I have the Tn minus 1, that's the present. I want to jump at the time Tn, and I have a bunch of times before, and I know the state at T1, T2, and so on. And so the jump does not depend on what comes before. It only depends on the present that will determine the future. Even if I know all the states before, that is not relevant information in the conditional probabilities. So even if I put there, I have the conditional independence on these previous states. And so the probability to reach a state at time Tn only depend on the closest previous time that you specify and the state I that you specify. Okay, that's the Markov property. So it means that I can define now the probabilities for the process only in terms of jump probabilities over specific times. I don't need, if I have the state at a given time, I know all the probabilities of jumping to any other state in the future. I don't need to know what's coming before. That's the Markov property. Okay, so now with this, we have something that's very similar to what we had yesterday, namely a transition probability. And so I'm going to write this now. The transition probability is very similar. What we have now is, I'm going to write as pi ij, but now we have two times, the starting time and the time that we're ending up to. So this is the probability to end up in the state j at time t, given that I was at the state I at time s. And s has to be smaller than t. So you're jumping from s to t in time, from state I to j. So it depends on the starting site, ending site like we had before. But yesterday for the discrete time, we were only concerned with transitioning from over one time step. Here we can transition between any two times, s and t. Okay, there's a more suggestive probability notation, which is from the state I, make the jump to the state j at the time t, if you want, that's how. So you see all the variable S and T, I and J. So this is the most general transition probabilities you can write, but it's quite complicated because you always have these two times. What we'll consider now from now on are homogeneous processes. That transition probability does not depend on the absolute time, but it only depends on the time difference. Okay, so this is a homogeneous process. Homogeneous Markov chain is one for which this does not depend on S and T as such, but the pi ij st is only a function of the time difference. So it's the same as if you started at 0 and you make a transition t minus s. Okay, so the picture that we have is time is here. I start at s. I want to end up at t. The probability does not depend on the absolute times, but only on the time difference, t minus s. If you have this property, and then we have this property in many cases, you say that the Markov chain is time homogeneous, or is homogeneous, or is time independent. Okay, and then this just simplifies the whole analysis. You can come back to this if you want, but the whole theory will be much simpler for this. So if I have this property, then what I'm going to write is this. Since the transition probability only depends on the time difference, we can actually dispense from having two time indices. So the notation I'll be using from now on is the following. I'm going to write now only pi ij t. So this is the probability to go from ij in a time t, in a time difference t. So this is the probability, say, to go from 0 to t. So you go to j, starting from x0, x0, at time 0, you're at pi. This, for a homogeneous chain, will be the same as saying it's t plus s if you start at the time s. Okay? So this is the homogeneous Markov chain. If I start at time s, I'm going to go t forward in time, so this is only the time difference. I go from I to j. It's the same starting from time 0, from I to j, ending up at time t for xt. So it only depends on the time difference. This is the homogeneous property. You can also write this, I write this in the notes. You go from I to j in a time duration t. This is the homogeneous property. You have this implicitly in quantum mechanics when you consider Hamiltonians that are time independent. Okay, the transition in quantum mechanics does not explicitly depend on time; it depends on the time difference. So here we have the same. Okay, so now we have this transition matrix. It's very similar to what we had yesterday. The only difference is that you see it depends on the time difference. But this is a conditional probability. This is a transition probability. So it has many of the properties of the transition probability that we've seen yesterday. So let's write them down. So in matrix form, what we have, we can write, we have a big matrix T, which is the matrix containing all the elements. Okay, but now we have a matrix that depends on time. It's called it's a stochastic matrix. What do we have in terms of properties? We have many properties for that matrix. First one is that pi 0 is the identity. Okay, why is that? Because if you're in a state and you say, what is the probability to transition in time 0? This is 0, so you're always staying in the same state. So the probability to stay in the same state is 1. This is what is mean. The next one is the elements are probabilities. So we have elements that are positive in between 0 and 1 for all ij, and then for all time. So this is a stochastic matrix. And moreover, we have the same property that we had yesterday. if you sum over all the j's, this is equal to 1. This is a normalization of probabilities, and now this is true for all time. So we have a stochastic matrix. And the last one, which we didn't have yesterday, but it was there implicitly, is that if you're looking at the probabilities for jumping over a time interval s plus t, you can decompose this first as the probability to make a transition in time t first, and then the probability to make another jump in time s. But this is a matrix product. See, so this is a big matrix containing all the probabilities of making a transition in time s plus t. What I'm saying here is that this is the probability of reaching some states over a time t multiplied by the matrix of probabilities for making transitions in time s. This is what we call the Sony group properties. You have the same property when you look at propagators in quantum mechanics. For propagators, if you have a propagator for propagating your state in time t plus s, this is you first propagate in time t and then you propagate in time s. You can do the other way around too. You can propagate in s and then propagate in t. Okay, and this is in fact, that Sony group property is the Markov property. Okay, but again, this is a matrix product. Okay, so this is the basic object to define the Markov chain. It characterizes like fully the Markov chain. It gives you all the probabilities, and in particular, it will give you the probability to reach a certain state at a certain time, which is what I want to discuss. So we have that transition matrix, and then we also have the probability vector that we had yesterday. What is the probability vector? The probability vector is the vector containing all the probabilities of reaching a given state at a given time. So I'm going to write that probability like this. This PJT is the probability to be in the state J at the time T. Ultimately, this is what we want to calculate. Given the Markov chain, given the dynamics, we want to be able to calculate the probability of reaching a certain state at a certain time. This is the object that we want if we want to make predictions about the stochastic process. Okay, so I have a probability for each of the state J at any time T. So now I can put those into a vector, and I'm going to write this now as vector PT. This is the vector with the probabilities for the state 1, the probability for the state 2, and then so on. So this is the same probability vector that we had yesterday. It's a row vector. We follow the mathematician's convention here. Yesterday, what I had was P vector sub n for the discrete time index. Now I have P vector with the continuous time index T. Okay, but it's the same object. Moreover, we have the same propagation equation. If I know the initial state, the initial probability, I can find the probability at any other time by saying the probability to reach the state J at time T is the sum over all i's of going from I at time 0 and to go from I to J in a time T. Okay, so this makes sense. The probability to reach the state J at time T is I can start from any state I at 0, and I have to multiply by the transition probability of going from I to J in the time T. So this is a generalization of what we had yesterday. Yesterday, it was only one time step. So at the next time step, we start from the previous time step, but now here we start from the time 0, and then we look at any time in the future T. If you look at this, this is again a matrix product, so I can write this down as a matrix product. I'm going to write this as P vector T is the P vector 0 and then the matrix T. So this makes sense. The initial distribution at time 0, I propagate it as row vector times matrix to obtain the row vector of distribution of the row vector distributions of the row vector of probabilities at time t. Okay. Now, because of the semi-group property, the Markov property, I can also write this as, instead of starting at 0, I can start at any time s, and here I will propagate with t minus s instead. Okay, so if I start at time 0, and I want to reach a time t, I can make a full transition from 0 to t, or if I know the state at some time s, intermediate time s, I can make a transition instead from s to t. And so I start at s, and so the remaining time for the jumps will be t minus s. So this is the Markov property. Okay. So now I have everything. I have the state space, and the process now is completely described by the transition probability, which depends on time. That's the pi t. If I fix the initial distribution for starting in the different states, I can calculate the probability distribution for any of the states at any given time in the future. Now, the problem you see is, how do I write down that pi t? What's in pi t? How do I actually construct the pi t for a given process? And this is what I want to discuss. So for continuous time, what we'll see is that we in fact don't, when we write down a model, a continuous time Markov chain model for a given physical system, we don't actually specify pi t. What we'll specify instead are probability rates, so probability per unit time, and from these rates, we can actually get pi t. Okay, so it's simpler to define the transition rates. We'll see what a rate is, and then from the rates, I can construct pi t for any time. Okay, just question. Okay, it's good. Okay, so this is the next section. This is called the generator. And in quantum mechanics, we have the same, and I'll explain what the similarity with quantum mechanics is once I finish introducing the generator. So this is section 3.2, the generator. What I want to show ultimately, what I want to reach, is this result that pi of t, that matrix of transition probabilities, is actually the exponential of some matrix, which we call the generator. And compare this with the propagator of quantum mechanics. The propagator of quantum mechanics is minus I, you have the Newtonian, you have the time, and then you divide by h bar. And then you might have heard this, the generator of the evolution in quantum mechanics is the Hamiltonian. For us, the generator of the evolution for Markov process is this matrix G, which is the generator. Okay, so this is what I want to go. This is the goal of this section. And the way to reach this is to consider the probabilities over a very small time interval, delta t. If you do this, then you can write as a Taylor series that this is the pi at 0 plus some matrix delta t, matrix G multiplied by delta t, and then you have corrections delta t squared. So we're doing a Taylor expansion of this result. And I'm doing this because I want to define what that G matrix is. What is pi 0? We've seen this before. This is the identity matrix. And so I'm left with something like this. Okay. Now I'm not going to go into all the calculation. It's quite, when I present now this section in my own course, we actually spent 2 hours on this, deriving the consequence of this and what this means. I know these are probabilities, and so I want to define what this is. But you can kind of see where it's going to go to, because these are probabilities and G is something multiplied by time. So G will be something like probabilities per unit time. Okay, so I'm going to skip a lot of the calculations that you see in the notes. And what I'm going to present now is only the last result, which is what that G is, the generator. So the generator contains 2 ingredients, 2 terms. you have the transition rates, and then you have the escape rates. And again, I'll try to explain what these are. So the complete generator, maybe I can write it here. The generator is a matrix, right? Pi is a matrix, so the generator has to be a matrix. So the generator is a matrix, so we write it as a matrix. It's the matrix of Gij. It contains two terms. You have off-diagonal terms, which we're going to call Wij, for I different than j. And then you have diagonal terms, which we call the escape rates. Okay, this is the delta, just to emphasize that this is diagonal. So this is off-diagonal, and this is diagonal. What are these? So we have the first one. We have the transition rates. Transition rates are the probabilities per unit time of making transition between the state I and j. So you can find these. So this is the limit when delta t goes to 0 of making a transitions from I to j in delta t divided by delta t. So I can rewrite this as the limit when delta t goes to 0 of going from I to j in delta t divided by delta t. And this is true for when I is different than j. You're making a jump, really. So this is a definition of the transition rate. Again, is pi ij delta t is the probability of making a jump from I to j in a very small time, delta t. If you take the limit and you divide by delta t, in a way you take like a derivative. So this is the probability per unit time of making a transition. And this is emphasized here. This is the probability of making a transition in the time delta t over delta t. This is the transition rate. So this is the off-diagonal part of the generator of diagonal contains all of these transition rates. This is the diagonal part. What is the diagonal part? The diagonal part is what we call the escape rates. The escape rate, just make sure that I'm writing this correctly. The escape rate now is just a number assigned to each state. It's not a matrix. This is the sum of all the j's different than I of ij. Okay, so this is the total, the escape rate is the total rate of leaving I. Okay, so this is the total rate for leaving the state I. So you have that total rate for each of the state I. You look at where you can jump to. You sum all the transition rates from I to j. You sum over j. This is the escape rate. With this, you have everything. Okay, so in fact, when you define a model, a continuous time model for a physical process, you only have to define the transition rates. And these do not depend on time, so that's the advantage now. These are time independent. They just probability per unit time of making transitions. So that's really the basic object that you want to define, to specify in a model. Once you have those, you can define also the escape rate. And with the transition rate and the escape rate, you just put this in your matrix, and that is your generator. And with the generator, you can find any probabilities forward in time. Okay? Okay. There's a property of the generator that I'm not going to prove, but you can check in the note, which is that the sum over j of Gij is 0. Okay, and that comes from the normalization of probabilities that we had for pi. The fact that pi is normalized in the rows means that the rows here, so the row sums, are all equal to 0. And this comes because we actually put the escape rates in the diagonal. So if you sum everything and then you just subtract the diagonal, then you get 0. Okay, so this is proven in the notes. Again, I'm skipping lots of things here in between defining the generator with the Taylor expansion and actually getting there to the expression of the generator. But we don't have time really to see this, but it's in the notes, and feel free to ask me questions if you have any questions about that derivation.
Something very quick. Hi.
Yeah.
So this existence of generator, is it extra imposed condition, or does it somehow follow from the fact that like transition probability at 0 is identity, and should we also impose that it's differentiable, the transition probability? Or
Yes. So this is a technical condition, if you want, which I'm not, it's in the notes actually. So in a way, you can write the generator as a limit when delta t goes to 0 of the matrix, transition matrix minus this. So it's really the existence of the derivative. So that derivative has to exist in the matrix form in order for the generator to exist. Okay. So this is actually a condition that you'll see in maths textbook. They'll say that you have that differentiability property in order to define the generator. Here we just skim over this. We just go straight to saying that the generator exists, and from the generator, we can define the process. In fact, in physics, what we do is that we specify the generator in the first place. So implicitly, we always have that property because we will build the transition probabilities from the specification of the generator. So the generator for us is there.
Yes.
Okay, there is a question here. What if the first order term G in the expansion of pi is 0? So again, it ties into this question. If we have the differentiability property, G will be non-zero. If you say that G is 0, it just means that your model is trivial. All transition rates are 0, and so the matrix is just a matrix of 0. For us, what we'll do again is that we'll always specify a model by specifying those rates to be non-zero. In fact, we'll specify only the non-zero rates, and so the model will make sense. And from these non-zero transition rates, we can define the escape rates, and from these two, we can write down the generator. So I'll see some examples actually in a minute where I specify the rates, I can write down the generator, and then we'll be able to write down the transition probabilities. There's a question here. Can you elaborate?
Maybe if
sorry?
According to this question, I was just wondering if there are models where G0, but it's the next to leading order term that is non-zero, like the term in delta t squared.
No, this doesn't really make sense, because what this says also is that in a time delta t, you can only make one transition. You cannot make a double transition. Okay, so this is a way, there's a lot actually contained in that expansion. This is not so trivial, but when you do an expansion in delta t, you have to make the assumption that in a small time delta t, or as delta t goes to 0, you can only affect single transition. You cannot have a double transition. A double transition will be of order delta t squared. So if you have in any double transition can be decomposed as single transition. So there's a term here, but it's all determined by the generator in the first place. Okay, so it's not like you can have 0 and then you can have a non-zero term in the second order. If there's a second order term, there has to be a first order term. Okay, why do we have that property that the row sums are 0? We'll see this when we have some example. This comes because we have the property, the normalization property for the transition matrix. The fact that we have that property equals to 1, and you see pi is the exponential of G, if you transfer this property in the exponential, you have to have this property. Okay, and again, it's you have the derivation in the notes. I don't want to emphasize too much. We'll just take that property as a consistency property in the way that we define the generator. Another question, how is the expression of Ri, the escape rate, in terms of the transition rate is obtained? Is it a consequence of the normalization condition? It is in a way, but it really comes from here. If you know this, you know these are transition probabilities, so you know that there's a diagonal part and enough diagonal part, and then for consistency, you have to have this. And again, this is defined in the notes. So what I would say is, take this as just like given there, but go to the lecture notes and you have one page of derivation actually leading to that result. So it's not so complicated, but you really have to go through to do this. But I don't want to actually go over this. It's too much mathematics there.
Okay. Something actually connected to the previous question, I mean, the question which I asked. So the fact that this transition probability is differentiable, from here it follows that the state vector has like linear equation first order in time, t. So, I mean, is it always needed that it has to be first order in time to describe like Markov chains, continuous Markov chains? Can it be like something fractional or like higher order derivatives? Why is this constraint needed actually?
What constraint again?
The fact that like pi has to be differentiable in the normal sense.
It's just about, I think it's just a continuity condition. You see, if pi is smooth in time, you can take the derivative. You don't need to go into fractional derivatives or anything like that. It has a derivative. And so you can build a Taylor expansion. What you want to understand is that, okay, we have this transition over any given time in the future, but it's continuous in time. So what I'll do is that, as we always do in physics, I'll look at a very small time and I'll see what's happening. If I can understand what's happening over a very small time interval, I can just then patch up a long time interval as being made of small delta t. So this is what we're doing here. Maybe I can. So what we have is that we have that pi t that tells us how we actually propagate or making transitions over a whole time t. But we don't know how to build that pi t. So what we're doing instead is that we say, okay, let's try to understand what's happening over a small time interval, and then we can just concatenate these behavior to get the full time. Okay, this is what we're doing. Now, to understand what's happening over a very small time, what I'll do is just Taylor expansion for the small time. And this is just a smoothness property of the pi t, which is assumed there. And so having that limit is basically assuming that pi is smooth in time, which it is for all the examples that we'll see.
Hugo?
So does that mean that it's a simplifying assumption, but not necessary to do Markov chain, continuous Markov chain dynamics, right?
Again, if you don't have that smoothness of the Markov chain, I don't know what's going to happen. Maybe it's something more technical that you'll have to define. If the pi t is not smooth in time, you're going to have to do something else, which is, I think, way beyond what we'll see in the course. We can discuss this. I think it's a technical thing that we can discuss.
So you are also assuming actually it's independent at each delta t time interval, right? If it is interval at each delta t time interval, it's essentially a Poisson process, no? And
No, I'm not saying anything about independence.
I'm saying if you divide your time into within small delta t,
I can always make that this. It's not an independence
and
assumption.
then this transition within the delta t is independent of the transition before or after.
No. So here you see again. So this is the semi-group property. Don't think about this. This I can always write as I decompose the full probability of making transition from 0 to t as first making a transition in delta t, then making another transition in delta t, and then so on all the way to the end. Okay, this is the time homogeneous property, right? It doesn't specifically depend on time; it only depends on the time transition. So this is the Markov property, and here I'm going to have this n times where n is going to be t divided by delta t. Okay, so I can always do this. So what I'm saying is, to understand the transition probability for a full time t, I'm going to decompose the full time interval into smaller times interval, like we do a lot. This is a discretization that we do a lot in physics. And what I do is that I want to expand this time delta t. What's happening over a very small time? Well, nothing is happening, plus something small is happening, and that something small is all described by the generator.
Doesn't it automatically mean that it's also a Poisson process then? I mean, no.
Poisson process will be a particular Markov process, but it's not a Poisson process. It's a Markov process. This is a Markov property.
But if I ask what is the probability that there is no jump within a given time t, it's just 1 minus this to the power n, and that's how you get the Poisson distribution, no? In the limit.
Yeah. But so this we'll get to this when we look at the sojourn time or the residence time. Yes, but this is a property for the Poisson process if you want. But any Markov chain will have that property too.
So then,
just the way that I think we're just hinging on what we call a Poisson process.
Yeah.
Any jump processes will have that property.
Yeah, exactly. So.
Okay, is there any physical implication of the row sum of the generator between being 0? No, it's the normalization properties. So we want probabilities in the transition to be summing to 1, right? So any probability, if I'm on one state, I have a selection of states I can jump to. If I assign probabilities for the jumps, the sum of all the probabilities have to sum to 1. So that's just a mathematical requirement. That's also a physical requirement. And that property translates into having this property for the generator. Okay, because again, the generator is the exponential of the generator is pi. And another question, stopping after first order implies that in delta t, you cannot make more than one jump. Indeed. Is this constraint embedded in the original system? How does it allow more than one jump in a single delta t? No, so we do not allow more than one jump in delta t because if the time is small enough, you can only make one jump. If you have 2 jumps, it means that you're actually compounding 2 jumps. And so you can make that delta t even smaller to only characterize the first jump that you did. So delta t goes to 0, right? So in delta t going to 0, either you don't make a jump or you make one jump. Again, if you allow more time, you can make 2 jumps, but it just means that you have to reduce your time closer to 0 to only characterize that first jump. And that first jump will be then given by the transition rate. This is why the transition rates are only between one state and another, not between one state, another state, and then another state. This will be a double jump, right? So the transition rates only describe single jumps from one state to another. And this is all we need because the transition rates are in the first expansion delta t, where we describe only single jumps. From the single jumps, of course, there'll be double jumps, and then we'll get to see this. This is in fact included in the full pi t. The full pi t will contain many, many jumps, but the many, many jumps are all made up of single jumps. Can the transition rate depend on time? Yes. But we're not including this in the course. It's too complicated or there's too much notation. The transition rates here do not depend on time because we consider homogeneous Markov chains. You could have a chain which is driven periodically. In that case, the transition rates could be time dependent, and then the Markov chain is not time homogeneous. It explicitly depends on time. In that case, the pi matrix does not depend only on time. It depends on S and T, like we've seen initially. Okay.
Hugo, so you're calling it a semi-group as opposed to group because the inverse need not be a Markov matrix. Is that right?
Exactly.
Okay.
It's not a group in general, it's a semi-group because we'll see, especially when we have ergodic Markov chains, starting from any initial distribution, we get to the same station distribution. So we have the semi-group property forward in time, but there's no semi-group property backward in time because we have a contractive semi-group. So there's no inverse in that case. Okay. In some cases, I guess there could be an inverse, but that's not the Markov property. Okay. What I want to present now is the evolution equation. Or maybe I'll do one example first. Let's do one example. Here. The example is the two-state Markov chain. So we've seen that two-state Markov chain yesterday repeatedly, and then we can have the same thing also in continuous time. So you can have a process that can take two values, 0 and 1. We can also actually draw these two values like this now. But now for a continuous Markov chain, I do not need to specify the probabilities. I have to specify the transition rates. So here I'll define the transition rate to be A, and then the transition rate to be B. What is the generator? Well, the generator here will be a 2x2 matrix because I have two states. The off diagonal are the transition rates. So here, this is the transition rate 0, 1. This is the transition rate 1, 0. So here I'm going to have A, and here I'm going to have B. How do I fill the rest? Well, the rest are the escape rates. But the escape rates, in a way, you can just define them by having the row sum equal to 0. So the escape rate here has to be A, and the escape rate here has to be B. And there's a minus sign because the generator in the diagonal contains minus the escape rate. And this makes sense. What is the escape rate from 0? Well, you can only escape with A, so the escape rate is A. What is the escape rate from 1? It's B, so the escape rate is B. Okay, so this is the generator of that process. This is good, you see, because this does not depend on time. I'm only specifying the transition rates, and out of this now, I can define that pi t as the exponential of gt as a matrix exponential. Okay, this is, you would do the same thing in quantum mechanics if you were dealing with a spin and the evolution of a spin. Just the evolution of a spin is given by a 2x2 matrix. You give the Hamiltonian, so the interaction Hamiltonian between the magnetic field and the spin, and then the propagator for the quantum system is a 2x2 matrix, which is given by your 2x2 Hamiltonian, T, and then the h bar. Okay, so it's exactly the same. In quantum mechanics, you specify the energy, the Hamiltonian, but the energies, actually the Hamiltonians, specify the transition rates. Here, in a classical setting with Markov chains, I have to specify the transition rates explicitly. This is the physical basis of defining a model, define the transition rates. You see here, I'm not specifying actually the self-loop like we had yesterday, because I don't have to. I only have to specify the transition rates between one state and another. The rest actually is defined by the fact that I have this property, this normalization property, that the row sums are 0. Okay, so this is the basic example. We'll come back to that example.
Hugo, shouldn't the escape rate be A minus B for R0?
Again?
Shouldn't the escape rate for the 0th state be A minus B?
No.
Why is it just A? Because it's the total rate at which of leaving the state 0. So the total rate of leaving the state 0 shouldn't it be A minus B?
Yeah, it's the escape rate is only the sum of the escapes. So here there's only one escape rate from 0. See, this arrow here is not an escape rate for 0, it's an escape rate for 1. So the escape rate is the sum over all the j's different than I for the escape ij. Here I have, if I want R0, I need to sum only over 1 of 0, 1. So there's only one term, so the escape rate is A. Okay? We basically, the escape rate is only the sum of the weights of the outgoing arrows. Only outgoing.
Okay.
Okay? So if I have a state I, and I have many arrows out, this will be I1, I2, and then so on, IN. The escape rate is the sum of all of this. You do not sum the arrows in.
Okay. Yeah.
Okay? So here there's only one arrow out, so the escape rate is A. And then in the diagonal, again, you have minus the escape rate in order to have that sum 0. Good?
Yeah.
Okay.
Yeah. Okay.
Okay, now the last bit of theory I want to introduce before we go to example is what we call the master equation. The master equation is a differential equation for determining the vector of probabilities. And that's the basic equation that you will see actually if you read any chapters on continuous time Markov chain. And that's the section in my notes, is section 3.3. That's the master equation. Remember that we have the equation, the propagation equation that we had before. The probability to be in the state J at time t is a matrix product from I, and then you look at the transition from I to J t. And then in matrix form, I said that this was at time t, this is just the probability vector at time 0, and then you multiply by pi t. That's the propagation equation. That equation is just a propagation equation that involves pi t. What we want to see now is whether we have an equation that only involves the transition rates. And there is one. And the equation is a differential equation, and that's the master equation. So the master equation is d dt, I'm not going to derive that equation, I'm just writing it down, is the probability vector times the generator. Okay, and then you can derive this from this equation. Basically, what you're trying to do is take the derivative of this. Okay, and this is something I do in the lecture notes. It's only 4 lines, so I have a look there to see how I go from this to this. But if you have this, you have this. Okay, this is useful, you see, because again, the idea now for us when we write down a model is to write down only the transition rates. So we have the transition rates, from the transition rates we get the escape rates, and from the 2 we get the generator. Once we have the generator, then we have this. Okay, and then in the quantum mechanical analogy, this is nothing but I h bar d, the wave function, is equal to h, your wave function. So that's the linear equation of quantum mechanics, that's Schrödinger's equation. What we see here is that we have a linear equation also involving an operator. That operator is a matrix in our context because we're dealing with a discrete state space. Okay. Tomorrow, when we go into continuous state space, we'll see that we have exactly the same equation, but this operator is not a matrix, it's a differential operator, just like when you're dealing with Schrödinger equation with particles. Okay, so this is the master equation. It's just a differential equation that tells you how the vector evolves. You can write down the solution if you want. The solution will be P0 with the exponential of gt, which makes sense because I've said that the exponential of gt was the pi t, and it's exactly the propagation equation that we have. So this is just a consistency check. If you know the propagation equation and you know that the transition probabilities are given by the exponential of the generator, this is why we call the generator, because it generates the evolution of pi t, then you have the master equation. This is all equivalent. Okay, this is the master equation, but it might not be the master equation that you see in textbooks, especially in physics textbooks. The master equation that you'll see there is slightly different, but it's equivalent to this one. It's just rewritten in some other form. And I'll write the other form. The other form is d dt, the probability to reach the state J. This is given by 2 terms. It's given by the sum of I different from J, and there are 2 terms. There's the Pi, then you have Ij, and then you have minus Ji Pj. And this is so this is actually equivalent to this one. It's just if you use the definition of the generator and then you use the definition of the transition rate, you can get to that form. And this is subjective because it makes sense. The variation of the probability at the state J is either coming because you have a flow of probability from I to j. So this is an inflow from I to j, or the probability can change because there's a probability flow out of j. So this is the flow out, outflow from j, where you're going from j to any I. Okay, so again, if you look at the probability for the state here, it can come because there's some probability that goes in, or there's some probability that goes out. And this is what you see here. Variation of probability, either you're coming in from different state I, or you're leaving j to different states I. So that's the master equation. That's the most common form that you see in physics textbooks. You also see it in maths, but in maths they actually try to focus more on this because you have that it's obviously linear. Of course, it's obviously linear, but you have two terms. What you can do mathematically is that you can combine the two terms in the generator, and then here it's really just like it looks simpler as an equation, but it's the same. Okay, there's a question from Pierre. For any interval 2 times, can we have an infinite number of jumps in the interval from this construction? The answer is no. You cannot have an infinite number of transition rates, of transitions in a finite time interval because the transition rates are finite. So in a given time interval, you can only have, in an infinitesimal time interval, you can only have 1 jump at most. But when you concatenate those, you can only have a finite number of jumps. Okay, so the probability of doing an infinite number of jumps will be 0. And then you can derive this if you have rates that are finite. Okay. Where am I now? Let me look at my time. Started at 10:30. That's good. Okay, the last bit that we have to see, you see, so this is the main equation for this chapter. It's the master equation defined with the rates. And then we're basically at the same point that we were yesterday. We have an evolution equation for the probability vector, and now we want to solve this. It can have many solutions, it depends on the rates, but the physically relevant type of models that we study are ergodic. And ergodicity now here means that starting from any initial distribution, when you look at the long time limit, you get to a stationary distribution. So we also have that notion of ergodic process, which I'm just going to go very quickly over. So this is 3.4, ergodic Markov chain. There are many different Markov chains that you can write down. Not all of them, most of them actually won't be ergodic. You can write down some periodic Markov chains like we've seen yesterday. You can write down Markov chains that are not ergodic, but what we want to focus on are ergodic Markov chains. So an ergodic Markov chain, has a unique limiting stationary distribution. And again, I'm not putting what are the conditions that will make a Markov chain ergodic. I'm just saying that it will have a unique long time stationary distribution. What does that mean? It means that if you look at the limit when time goes to infinity, of that p vector t, it goes to a certain p star, and that p star necessarily has 0 time derivative. It doesn't change in time, so it has the property that if you apply g on that p star, it's equal to 0.
Hugo?
Yes?
Yeah, this answers to this Pierre's question. I mean, there's no upper limit of number of jumps, right? Because you can just make it finite. Only thing is that the probability also becomes smaller and smaller within that small interval, basically.
Yeah.
So, I mean, in principle, there can be infinite number of jumps, but probability of each jump is very small, basically.
Yeah. So what I'm saying is that the probability of an infinite number of jumps would be 0. So it does, you could imagine actually making an infinite number of jumps. It's just, as you say, the pi delta t becomes smaller and smaller and smaller. And so you have that product of many different probabilities. And so the probability will go to 0. Is ergodicity necessary for a unique stationary state? No, it's just in the definition of what an ergodic Markov chain is. An ergodic Markov chain will have a unique limiting stationary distribution. So it says, I'm going quickly on this. Sorry, it's the other way around. We have two concepts just like we had yesterday. We have the concept of a stationary distribution. A Markov chain could have one stationary distribution, could have many stationary distributions. Maybe it doesn't have any stationary distribution. So we have the stationary distributions are the 0 eigenvalue, eigenvectors of G. Okay, and so you have that concept of stationary distribution. The other concept is the limiting distribution, and so you have the time-dependent distribution. You take the time limit, and you're trying to determine whether it converges to something. Maybe actually this converges to something, but it depends on the initial distribution. So that limit for all initial distribution P0. So this is a very strong statement. Given any initial distribution that you choose for at time 0, when you take the long time limit of those distributions, it always goes to the same unique stationary distribution, which is the pi star. That's an ergodic process. Okay, which is fine because it just means that the process actually over a long time looks the same in terms of occupation probability, regardless of where you started it. And this, people would say you lose the memory of the initial state in that case. Okay, so where you end up does not depend on where you started. And this is in the long time limit. Okay, there's a lot more actually in my notes again. But have a look there. I just want to be brief on this because these are the processes that will be studied. I was wondering if this construction allows one to recover the jump distribution of infinite activity Levy process. Levy process is something else. Levy processes actually are part of a construction for jump processes. But they're actually different types of Levy processes. So the name Levy process can mean different things. So I'm not sure that I want to answer this. This is quite difficult, quite technical. There's a notion of Levy process, which is just a mixture of continuous space and discrete jumps. So that's called a Levy process. And there's something else, which is a Levy random walk where the jumps have a Levy distribution, like a Cauchy distribution. And that's very different. So we don't have this here. In this limit, an element-wise or uniform limit in the vector P. So this is element-wise, right? So this is a vector, and I'm saying that all the elements actually converge element-wise to that P vector star. So this is the limited vector in the same sense that you would, yeah. Okay. I think I'm ready now to go over some examples, and then we'll finish with this, and then we can take some questions. I have two examples, but maybe even more depending on the time that we have. And then it's something I've skipped there, which I want to go over. Oh yes, that's the page here. Before I go to the example, then I want to touch on something that Sanjib mentioned, which is what is the probability that you stay in a given state over some time? And this is important for simulating jump processes. And so this is section 3.5. This is what we call the sojourn or the residence time. Okay, and I'll do this and then we'll go over some examples. So the idea here is that you have time and you want to say, what's the probability of me staying in the same state over some time interval or time tau? And the way that we'll do this is that we'll just divide this in small delta t, and then we'll say, okay, what is the probability that I stay in the same state over that delta t, and then I'm just compounding the probability. So what I want to calculate is, what is the probability that I stay in the state I for all times between 0 and time. Okay. So I can write this in English if you want. Xt stays in I for time tau. This is the same as saying that over that time tau, I have no jumps. No jumps over 0 tau. This is the same. But this is the same as saying that I have no jump in delta t, and then I multiply this idea that I have no jumps in delta t with the next delta t, and so I'm going to have this to the power n being tau over delta t. So I have n time intervals. I'm looking at having no jump over all the time interval. This will be the multiplication. This will be the product of having a probability of no jump in delta t, no jump in delta t, and that's the Markov property, because the Markov property says that the evolution is only determined by the jumps probability. So if you're looking at the probability of having no jumps overall, it's the multiplication of the probability of having no jump in each of the delta t. The probability of no jump is pi I over some delta t, and here you have tau over delta t. Because pi I is the probability to remain in the state I. So that's the probability of having no jump into delta t, and I multiply by this. But pi I, if you look, that's the diagonal part of the transition probability. So it's got to be given by the diagonal part of the generator, and the diagonal part of the generator is 1 minus the escape rate. You have here t over n, and this is the power delta t. When delta t goes to infinity, to 0, this is actually the exponential. So when delta t goes to 0, this goes to minus Ri tau. So the probability to remain in the state I for a time tau is exponential minus Ri times tau. This is why Ri is called the escape rate, because it really is the rate for the exponential distribution of the occupation time. So the residence time for a given state is exponentially distributed. So what we have now is a kind of picture where instead of making jumps over delta t's, what we have, and I'm going to finish here before I go to the examples, is if you look at your state, think again at what I was talking about. You stay in some state for some random time, and that random time is exponentially distributed. So one way to simulate the process is that you start in some state, maybe the state 0, you throw a residence time which is exponentially distributed, and then you say, I stay in that state for that random time. And then you choose another state at random, and then you throw another residence time at random, which is tau 2. And then maybe another state. And so all these residence times are exponentially distributed. So it's a different way of picturing a continuous time process, is instead of thinking about different transitions over delta t, see the process as staying over random times in specific states and then jumping between states when it has to jump. Okay, and these times are exponentially distributed. So these tj's are exponentially distributed, the exponential random variables with the rate Ri. Okay, so the time that you're going to stay in the state I is exponentially distributed with the rate Ri. Good? Okay, so let me go to the examples for real now. Let's see if there's any question. No. Okay. Let me go back to the two-state process, and then I'll see the Poisson process that was mentioned by Sanjib. And these two actually will give you an idea, a very good idea, I think, about some of the problems that I have in the coursework sheet. So for this chapter, there's a coursework sheet, which I like a lot because it's a lot more physical than the first one that was presented yesterday. So the first two questions actually, for instance, in the coursework for this chapter has to do with nuclear physics and particle physics. So the one is about particle disintegration and the other one is about cosmic showers. So when particles come from outer space, hit the atmosphere, and actually the relationship with the atmosphere will create new particles. So you have these particle shower. Yes?
So the previous residence time calculation, so you're measuring the time from the time when there was a jump, from the last jump, right?
Yep.
If you measure in at a time in between two jumps, then it will not be the exponential. This answer will not be the true, right?
Yeah, that's a good point. So that residence time is really, you have to start calculating that residence time from the time that you arrive at the state. And then you're saying, from the time I actually in that state, what is the time, what is the probability that I'm going to stay there? So this is why the calculation is kind of varied, because I'm saying I should have said that I start at 0 in the state I, and I want to calculate the probability that I stay in I for all that time tau. It's different from what you're mentioning is that if I fix now, I say I'm here, what's the remaining time of staying there? This is different. Okay, so example, so 3.7, if I follow my notes.
Is the time from the,
yeah?
Is the time from the last jump, or it's actually, if I pick up any time segment, then what is the probability that there is no jump within the time segment, right? Even that is given by the same thing, no? Because what you are doing is basically each time segment, what is the probability that there is no jump? And you are just multiplying that and then taking delta t going to 0.
Yeah.
So I think since it is exponential, it need not be from the last jump, no?
I think you're right, actually, because you have that, it's the Markov property that's behind anyway. If you fix it,
exactly.
you know you're in that state, then there's nothing that actually comes before. So if you know, if you know you're in the state I at time t, and then you say, what's the probability of still staying in that state? It's still exponential.
Yeah, exactly.
But I think it's a bit, it's a technical point for the students. I think it's something we can understand. I'm not sure I want to explain this now. Okay. First example I want to cover is that two-state. So we've seen it, but I just want to go over it just to complete a few things. So this is the two-state Markov chain, which is also called the Bernoulli process. And in physics, it's also called the telegraph noise. Okay, so you have, now I'm going to change the variable. It's not xt, it's nt. Doesn't really matter. That's the state variable. It takes value 0, 1. So the picture for the process is something like this. And I have to define true rates because I have two states. I'm going to call them alpha and beta. So the generator, as I wrote before, will be minus alpha, alpha, beta, minus beta. This is the generator. So the process looks a bit like this. You have two states, 0 and 1, and this is your nt. And over time, what you can do is that you stay in 0 for some random amount of time. You transition instantly into the state 1, and then you do this, you do this. So you have these jumps between 0 and 1. So that describes in the simplest way the kind of laser that we were discussing yesterday, where you have a ground state and some excited state, and you're making transition from the ground state to the excited state at random time. So this is really a jump process where you have jumps now between only two states, and that's the Bernoulli process or the telegraph noise. Okay. So when I presented the example before, I only went as far as writing the generator. What I want to write now is the master equation. So the master equation for this process is, again, you would write the master equation like this, is the probability vector, which is equal to this. If I write this down now explicitly in components, what I have is the ddt, the probability to be at 0 for the time t, is beta probability to be at 1 at time t minus alpha probability at time 0 at time t. And this is the master equation in the other form that we've seen, and it makes sense. The variation of probability at 0, it's either I'm coming from 1 with rate beta, or I'm leaving 0 with rate alpha. And the fact that I'm leaving means that I have a minus sign. The time derivative of the probability to be at 1 will be very similar, will be alpha. Either I come from 0 with rate alpha, or I'm leaving 1 with rate beta. So this is the master equation. Okay, what there's actually, this is a simple equation. It has a solution, Pnt, and then you can verify that this is the case, is minus gamma t. I'll define in a second what gamma is. This is the initial distribution that you specify, plus mu n over gamma, 1 minus gamma t. And here I have two parameters. I have mu1 is alpha, mu2 is mu0, sorry. mu0 is beta, and the gamma is mu1 plus mu0. Okay, so that's the explicit solution. You can take this, plug in there, and then you realize that this is actually solves the master equation. And moreover, depending on your initial distribution, if you take time going to infinity, this will go down to 0, so you have that term. So the stationary distribution is P star n is mu n over gamma. Okay, because this goes to 0, this is the terms that kills the initial distribution, so you forget the initial distribution, this goes to 0, and then you're left with this mu n over gamma. So it means that the probability to be at 0 will be beta over alpha plus beta, and the probability to be at 1, the stationary probability, maybe I can write this down. Means that the stationary probability to be at 0 is beta alpha plus beta, and the stationary probability to be at 1 is alpha plus beta. Okay, so if you study your system for a long time, what you'll see is that on average, it spends beta over alpha plus beta fraction of the time in the state 0, and then over a long time, the occupation time, more or less, for the state 1 is alpha plus beta. Okay, so this is the meaning again of the stationary distribution. The stationary distribution gives you the long time occupation fraction for the different states. It gives you basically the probability to see the system in a given state in the long time limit. Okay. Okay, what I want to, before I erase this one, what I emphasize again is that everything is determined by the generator. I haven't actually written down the pi t. Once you realize that a continuous time process is all determined by the transition rates, that's all you have to focus on. You never have to write any pi t matrix, which depends on time. This is time independent because we consider a time homogeneous process, and with this I can write the master equation, and then it's all about solving the master equation and determining whether from the master equation you can see if the process is ergodic or not. There's a question here, can we calculate the total number of jumps from the initial configuration to the configuration at time using the generator matrix? The answer is yes. So this is something that I haven't calculated, but if you look at a given trajectory, you can calculate what's the probability that you do one jump, or the probability that you do 2 jumps or 3 jumps. It's a more technical calculation, but you can do this. What is the probability for there to be n jumps in time t? So that will be that, okay? And then we'll see it actually in the next example. It's mentioned in the chat now. that this is given by a Poisson distribution. Indeed, it's given by a Poisson distribution, and I'll show this in the next example. Okay. Okay. So this is a simple example. It's covered in the notes. It's also covered in the coursework. So have a look at the coursework if you're interested. And then actually the coursework goes into asking you to solve this to get to that solution. Okay. Next example up is the Poisson process. The Poisson process is also called a counting process, and we'll see why. But this is 372, the Poisson process. Poisson process, I'm going to define also the state as nt, and now it takes values 1, 2, and then so on. So it takes values on the integer, positive integers from 0 to infinity. By convention, we always take at time 0 the 0 state, and then what I'm going to write is that I've used annotation before. Pnt will be the probability that the occupation nt is equal to some value n, which is an integer. So what we have in terms of Markov chain is I have a state 0, I have a state 1, I have a state 2, and then it goes to infinity like this. And the Poisson process is defined as a process that has a constant rate for going up. So this is why it's called a counting process, because you're going from 0 to 1, 1 to 2, 2 to 3, but you're doing this at random. So the process will look at it like this. If you can simulate the Poisson process, you start at 0, you stay at 0 for some time, and then you're going to have a jump. And then you have jumps like this, and the jumps are always by 1. Okay, so this will be 1, 2, 3, and so on. So it's a counting process. It's a random clock. It just counts with random residence time, tau 1, tau 2, tau 3, tau 4, and then so on. What we want to calculate is what is the probability that at a certain time t, I hit the level 3 or the level 2 or the level 4. So I want to calculate the time-dependent probability. Well, for this, we have the master equation. So the master equation for this, if you have a look, I'm not going to write the generator here because the generator is trivial, right? There's only a constant rate to go up. That's the simplest Poisson process you can imagine. So the master equation here is quite simple, and t is the variation of the probability for the state n can be either I'm coming with a rate alpha from below, n minus 1, or I'm leaving n with rate alpha. So the master equation is just this. I only have one line of equation because there's only one rate. So the probability to be here is either I come from below with some rate alpha, or I'm leaving the state with the, and it's the same for all the n's. And then I have an initial condition. I said by convention, at time 0, I start at 0. So there's no probability for any other states. Okay, the solution for this, and this is also part of the coursework, if you want to work on this, I'm just going to give the solution. The solution is a Poisson distribution. It's lambda t to the power n, e minus lambda t divided by n factorial. So that nt is a Poisson random variable of rate lambda t. Okay, so the number, so here it's clear that the process, because it's a counting process, if you want to calculate the number of jumps that happens in the process, it's only where you are after a time t, because you're jumping always by 1. So it counts effectively the number of jumps that it has over a time t. That distribution is a Poisson process. So that answers the question before. If I take any other Markov chain and I want to calculate the number of jumps that I do over time t, what is the distribution of that random variable, the number of jumps? The answer is a Poisson distribution, which is going to be more complicated, of course, because you don't have a single rate lambda for the jumps. You have now a compounded rate lambda. And so this will be slightly difficult, but it gives you the idea that underlying the number of jumps is a kind of Poisson process. Okay. This is the basis of one of the questions in the coursework about the cosmic shower. If you should, I think this is an interesting question. So have a look at the coursework there. You have the solutions again, they're typed. And then there are many questions about simulations of these processes. And then also you have the Python code for the solutions. I think the time is more or less up. So I think I'm going to stop here. There are more pages to the chapter, especially about simulation. And then we'll come back to those pages on Thursday when I discuss simulations of Markov processes. But for now, I think I'll just close this chapter about jump processes. And what we'll do tomorrow is to look at Brownian motion and stochastic differential equations. So what we'll do tomorrow is to move to processes that are continuous in space. Okay, and that will kind of close the loop of the processes that we've seen. Yesterday, discrete space, discrete time. Today, discrete states, continuous time. And tomorrow, we'll see continuous space, continuous time. Good. Questions? There's questions from Sorav. Would the rate lambda for a general Markov process be the sum of all the transition rates? That's, yes, it will be basically like a mean rate for all the jumps. Okay, I think this is covered actually in one of the textbooks that I mentioned as a reference for the course. Other questions?
Hugo, I had one question. It was related to when we were doing the expansion of the Markov matrix. So if you have a Markov, the question that I asked at the time, that so if you use that it is a semi-group, that at m, that the pi at t0 is 1, and you use that it's uniform continuity, that it is, then isn't it that it has only one representation, that it's e to the power t times the generator?
Yeah.
And then that would already answer this question, that you could, at the linear order, you cannot have just 0 and then assume that the higher order, like t square order. So the fact that it is a semi-group and it's a uniform continuity at t equal to 0 gives you that it is by definition, it's e to the power t generator.
Yeah, yeah.
Okay.
But then I guess you see, so there are two aspects to that result. Is you can phrase it mathematically as asking uniform continuity, but what it means in terms of probabilities or in terms of the process itself is that you're only looking at single jumps.
Yeah.
There's no double jumps. Yeah.
Yeah, that's
the uniform continuity. Yeah.
Yeah. Okay. Thanks.
Yeah. What process would you see for spontaneous emission? So that can be modeled as a continuous time Markov process. Yes. And that's the first question in the coursework. So have a look. The first question of the coursework is about nuclear reaction where the particles can disintegrate. And so you have a certain rate of particles actually disintegrating. And then you have more particles, say, that can come in from different beams. And maybe you've seen this in nuclear physics, but nuclear physics will tell you that if you have a bunch of radioactive material, then the radioactivity will decay exponentially and then this is all defined with the half-time life for the radioactive material. This is actually when you say that the material, the radioactivity decays exponentially in a deterministic way, that's only a macroscopic phenomenon. If you take only one atom, one radioactive atom, then it can emit alpha particle at random times. And so at the microscopic level, actually, can be described as a Markov chain in continuous time. And so this is the subject of the first question. And if you put many of these particles together, what you'll see is that although every particle emits alpha particles at random times, they actually combine to emit really a beam of alpha particle that looks deterministic, and it is exponential. Okay, so again, this is the subject of the first question. Have a look at that question in the coursework. And the second question, again, is on this comic shower, which is a Poisson process. There's one particle arriving, it just splits in two, then each particle can split in two. This is a bit like a chain reaction, and then it's a Poisson process. You want to calculate the probability of receiving in your detector and such particle after starting with only one particle. Yeah.
Hi. I have two questions. So one is, if I want to fit this framework of continuous time Markov chain into continuous time random walk models, if I just say that waiting time is exponentially distributed, is that enough, or like do I need to do something more?
No, even for random walk, it depends how you define a random walk. It's actually an example I have in the lecture notes. So the example starts with the Bernoulli process, then you have the Poisson process, and then if you go down, actually, I look at the bird-dead process, which is a Poisson process where you have different rates of going up, but then you also have rates for going down. So you have birds and deaths. And then just after, I think it's after, not quite, yeah. Then there's a model of queues, but these models can be a random walk. So maybe I can write down actually this. This is maybe relevant for many students. A random walk that you would have is you have the integers on which you can jump on. And if we follow what we've done yesterday, is that you have the positive integers and the negative integers. And then you can define the random walk in many ways. Maybe the simplest one will be you have constant rates of moving up. And then you have now constant rates for going down. This will be the continuous time equivalent of the random walk that we saw yesterday. And now the generator here is this big matrix that has a line of alpha, a line of beta, and the diagonal will be minus alpha minus beta. And then you have zeros everywhere. Okay, so this is an infinite by infinite matrix, but you can write the master equation, and we'll have only two components.
Okay, thanks. So I have one more question. So if I look at the continuous time Markov process, and if I only observe at some discrete times, I can say that, okay, it's exactly like the discrete time Markov process.
Yes.
Is there any like reverse procedure? Is it possible, like in asymptotic limit for like discrete time Markov process? Can I sort of do some coarse graining and arrive at like some continuous time description? Is it possible for always, or are there any constraints?
I think that there is an answer to this. Maybe I can explain the first part of your questions for the other student, which is a very good remark. If I look at the continuous time process and I discretize time in some way, it doesn't have to be small time, but if I have a process that evolves continuously in time, a jump process, and then I say, I will observe that process only at specific times, say like here, 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 here. So I choose a certain time interval, I don't know, like tau. Tau is not good, it looks like it's a random time, but it's not. If I look at the process in the stroboscopic way, like this, it's a Markov chain. So then what I do is that I have those states. So if I map those states as a Markov chain, like this state, that state, that state, that state, this is a discrete time Markov chain as we've seen yesterday. So that's a good point. If I discretize in time the continuous time Markov chain, it's a discrete time Markov chain. It keeps the Markov property. Now, I think what you have in mind in the other way is that can I make a discrete time process now as a continuous time process? Well, there's the way that if you take delta t to 0, yes, that's how we actually imagine the continuous time process. We just discretize time with delta t, and then we took time delta t to 0. So that's one way. Then it's not like if you interpolate the state, though, this is different. I don't think you get a Markov chain in that case. So I would say as an answer that if you have a discrete time Markov chain, it's only by taking smaller time intervals that you could maybe actually converge this to a continuous time process.
So that means for the homogeneous discrete time case, it's possible. So for inhomogeneous, I can encounter a situation where maybe it's no longer differentiable or something like that. Can that happen?
The time dependence, the fact that you're not homogeneous is not really a problem at the level of being differentiable. It's just that the matrix itself, the generator, will be time dependent because your rates will be time dependent. To be non-homogeneous only means this. It means that the rate from jumping from one state to another actually depends on time. In many physical situations, that will be the case. For instance, if you drive periodically a system, then the rates have to depend on time. And this is relevant in biophysics. For instance, if you look at some chemical reactions, the rates can be changed periodically. And so you have rates, transition rates that do depend on time. Then the generator is a time-dependent object, which means that the matrix pi here is not just the exponential of the generator, it's the exponential of the time-ordered generator. Okay, maybe you've seen this in physics if you do path integrals or quantum physics. If you have time-dependent Hamiltonian, then the propagator is a time-ordered and exponential integral, and here we have the same. Okay,
yeah, I was worried about the reverse process. Like if I start with discrete time, discrete space stochastic process, this Markov chain process, and then if I say that it's inhomogeneous in the sense that at different jumps, like the transition probabilities are different. So in that case, I mean, it seems like maybe it's not always possible to go to the continuum description. In the other case, where for after n jumps, like the probability goes like pi, transition probability goes like pi power n. It sort of makes it like it smooth dependence on n. Maybe it is valid to describe the continuous time limit.
So, I mean, I would say that it's very uncommon. I haven't seen this actually going the other way around. I think that the natural thing to do is that when you have continuous time, then you discretize into some observation time, and then you get a discrete Markov chain. That's a natural thing that one can do. For instance, if you do biological experiments, then you have some process actually that evolves continuously in time, but you're doing measurements only at specific time. And so if you want to build a model of this, then you'll be using discrete time Markov chains. Going from discrete time to continuous time, unless you imagine the discrete time to be just a discretization itself of continuous time, is that's not something that I've seen at all, actually.
Oh, yeah.
And imagine when you have the discrete time Markov chain, and we're seeing that what's the probability to do n jumps, then it's pi to the n, but n is a discrete index, it's not a continuous index. So you can't say that pi n is continuous in n. N is ultimately discrete in that picture.
So, but because pi is a positive definite matrix, so I can always take logarithm of it and exponentiate. So that way I can introduce some generator. I mean, typically if it is a homogeneous process.
Yeah, if you want, but I don't think that's the right picture to consider. That everything is contained in pi anyway. You see, pi is the basis of the description because pi contains the transition probabilities. You don't have to invent a new object to actually describe pi. The reason why we introduce the generator is because pi for the continuous time depends on time, but we'd rather have something that is not time dependent, and so that's the generator. And if you have the generator, then you can build up pi for any time. Here we have pi in the first place.
So why I was worried about it is like if I am trying to numerically compute some quantity for a discrete time process, and if it is inhomogeneous, I might have to multiply a lot of matrices, and maybe it's not a good numerically stable process. I'll encounter errors. But if I'm only interested in asymptotic states, maybe some way something guarantees me that I can write down some continuous process and directly solve the differential equation, so which might be much more stable process.
I guess when n is very large, no, then like for example, you go from random walk to the diffusion equation in some effective way. I guess one can do it, but then you have to also these states you have to coarse grain somehow, and full observation time has to be quite large, I guess. I mean.
Yeah, but we'll see this on Thursday. Even for a long time, there's no problem because it is a positive matrix, but it's a stochastic matrix too, right? The elements are between 0 and 1. So even if you do many products, everything is well behaved numerically. It never diverges. You don't have exponential divergence in the products. So actually, long time limits are very stable. You can simulate them in many ways, and even in terms of matrix product if you want. Of course, computationally, you might not want to do all these products, but then there are better ways actually to get stationary distribution. You can just simulate the process directly. You can simulate a bunch of them, and this is what we'll see on Thursday.
Okay. Yeah, thank you.
Yeah, I think that's about it, no?
Can I ask a question?
Yes, of course.
The second order term in the expansion of pi, does it hold any meaning, physical meaning, or is, I mean, I understand it's not directly useful.
No, it has a physical meaning. It will be, so pi t contains everything, right? Pi t will give you all the probabilities of reaching a state I to j. So maybe I can write this down. This is important. So if I look over a time t and I start an I and I want to say, oh, what's the probability to end up in j? So I can do many things in between. I can even visit j for some time. And then, but I want to say, what's the probability of reaching j from I? This is given by pi ij. Okay, so this matrix contains all the information about the trajectories that will take you initially from I to a certain j at the final time that you consider. So it's a multi-jump processes. It contains a lot of information about what's going on between 0 and t, and it gives you ultimately the probability to end up at j at time t. So when you look at the expansion in terms of delta t to be pi 0, then you have the first term, then you have another term, let's call it h delta t squared. Then this is the information from the single jump. You reach j from I in a single jump. This will be the information of reaching j from I doing double jumps, then triple jumps. So you have to see it in a kind of perturbative way where you can reach a certain state by doing multiple jumps anywhere, or and then the first order term is the term that describes only the single jumps, and so that's why that term is only described with the transition rates. It's a transition rate between only two states. You don't look at double transitions.
Yeah, thanks.
Okay, but I would say, again, this is not something I've seen them actually at all, is that it sort of makes sense if you think about Feynman diagrams and doing perturbation calculation, but once you have the generator, you have everything. Because once you have the generator, then you can write something like this. Of course, whether you can calculate this depends on the model that you have. If you have many states, then this is a huge object. And so taking exponential of matrices, of large matrices is very costly, but you can still define this.
Yes.
Good. Then there's another question. Coming back to Pierre's questions, can we construct a Markov chain that allows an infinite number of transitions in a finite time? Yes, you can. And if you scale your rates, and if you have time-dependent rates, so you can build very artificial examples if you want. But you can build something like the Zeno effect, where the transition rates between I and j actually scales like a constant and just say scales linearly with time. So it means that, no, I want the other way around. As time goes to 0, the rate becomes very high. So if you take the small time limit expansion, then it won't be differentiable. And then you'll see that when you take smaller and smaller time, you just have more and more transition. And so eventually you'll have an infinite number of transition. So you can have this if you want. These are very singular processes. For most, if you have a process that has fixed rates, you don't have that probability because the distribution is Poisson. So the Poisson distribution for the number of jumps in a given number of time actually will assign 0 weight for an infinite number of jumps. Okay, have a look. Again, for the Poisson, we've seen that the number of jumps in times t is lambda t to the power n, and then exponential of minus t, and then n factorial. By scaling lambda with time, you can make this actually infinity. And you can put more and more weight for the very large n, but this will be a singular system. Okay, I don't think it would be such an interesting system anyway. It's very degenerate. You have lots of jumps, and then with probability 1, you have an infinite number of jumps. Other questions? Good. Okay, I would encourage you again. I'm really blabbing about this, but have a look at the coursework. You really get to understand Markov processes, of course, like anything else when you learn, by practicing the material and really like stumbling on some calculations. So there's some calculations there in the coursework. They're not so difficult. And there's some numerical questions that we'll try also to get to when we, on Thursday, when I cover simulations of Markov processes. And if you have any questions, feel free to send me an email. I'll be happy to answer. I could not join, unfortunately, the exercise session yesterday. I don't think I'll be able. It's quite a busy week here with, we're just entering a new phase of lockdown, so the teaching has to be changed in some way. So I'm quite busy, but feel free to send me emails and I'll try to reply as quick as possible. Good.
Okay, I guess so. I'll see you tomorrow.
Yeah, I'll see you tomorrow. You have a good day, and then I'll see you tomorrow.